Hey Internet, welcome to Solid Mechanics tutorial. This is a made-up question not found in your textbooks. We've got 4 vertical links, 9 by 38 millimeters, uniform rectangular cross-section. Each of the 4 pins has a 18 millimeter diameter, so 2 at the top and 2 at the bottom. Okay. We want to find the maximum value for the average normal stress in the links connecting to Y and W, and then points Z and V. Okay, so step 1, convert this 3D drawing into your FBD, your free body diagram. Step 1, draw your free body diagram. This will help you visualize the problem. We're going to analyze the horizontal link. Note that W and V is directly below Y and Z respectively. Okay. So we've got 21 kilonewtons at point X. The length of XY is 0.026 meters. The length at YZ is 0.041 meters. Step 2, list all the given variables, find the unknown. So I just set the given values, and we're trying to find the average normal stress for YW and ZV. Step 3, find the normal stress formula. So sigma is equal to force divided by area, F divided by A, and that is the Greek symbol, sigma, for stress. We're going to divide it into part A, part B. We need to find the forces and the areas respectively. Step 4, find the force for point Z. So sum of the moments is equal to 0. So point Z is here. We are going down to counter the kilonewtons at point X. So that will be positive because it's going clockwise in a circular motion. So that's the standard convention. Okay. So we've got length YZ multiplied by the unknown force that we're trying to find, which is force YW, minus the combined length of XY plus YZ multiplied by the force at point X. Okay, so the combined length is the total length of the horizontal link, and the force is 21 kilonewtons at X. We set it to 0, and then we rearrange. The force YW is equal to 34,317.07 kilonewtons. The force is positive, so the link will be in tension. Alright, so step 5. Find the area for the tension loading for the link YW. So now they are talking about the vertical links. So the link width multiplied by the link length minus the diameter. So if we refer back, we're talking about this link right here. Okay, so it'll be 0.8 0.008 meters multiplied by 0.038 meters minus 0.018 meters, and you'll get an area of 0.000160 meters squared. Since there is 2 parallel links, as you can see, one over here and then one at the back, we have to multiply by 2. So we'll get a net area of 0.00032 meters squared. Now we can backtrack and solve part A for the normal stress at the points YW. So this is the force that we found in step 4 right over here. The net area is what we found over here. So you'll get 107 million newtons per meter squared, but we want it to be in megapascals, so we divide by million, and we'll get 107.24 megapascals for the average normal stress at points YW. Alright, so that's part A. Now for part B, we want to find the force at point Y, so right here. Now the force will be going counterclockwise to counter the 21 kilonewtons. So let's do the calculation. Counterclockwise moment is negative. Be sure to add your negative sign in front. This is important. Okay. So it will be the length YZ multiplied by the unknown force, which we're trying to find, minus the length XY, and multiplied by the force at point X. So why is it XY? So as you can see, we are bending it this way. We're bending this side counterclockwise to counter the force. Okay. So we will get the force, once you rearrange, of ZV is equal to minus 13,317.07 newtons. Since the force is negative, the link ZV is in compression. We find the compression area. So it will be the width multiplied by the length. Because if we go back up to the 3D drawing, it is pushing these vertical lengths downwards. So we don't need to subtract the diameter of the pins. Okay. So we multiply these together, we'll get 0.000304 meters squared. Once again, you got two parallel lengths, so you need to multiply by 2. You'll get 0.000608 meters squared. Now we can backtrack and solve for part B. So we want to find the normal stress for point ZV. The force is what we found in step 7 right here. The area is what we found in step 8. Actually, it's, yes, right here. And we will get minus 21 million newtons per meter squared. Once again, we divide by 1 million to get it into megapascals. So our final answer is minus 21,000,090 megapascals for the average normal stress of point ZV. Disclaimers, the method is correct. However, I do make calculation mistakes. I encourage you to solve it yourself and see if you get the same answer. Now, before we leave, I highly recommend that you save this video onto your PC, just in case this video or channel gets taken down. While I follow all copyright laws, sometimes things happen. If you're on a Mac, use the Mac equivalent of Snipping Tool. If you never used Snipping Tool before, follow these instructions. Click on your icon in your taskbar. If it's not there, go to your Windows search, type in Snipping Tool, open up the program. Click on the video option, click on New. Left click and drag the rectangle to cover the YouTube screen. This is just an example. Hit the start button in your Snipping Tool, wait for the countdown, hit the replay button on YouTube, let the video finish. Hit the red square in Snipping Tool to stop recording and then save your video. Thanks for watching. Hope you had a great day. Be sure to like and subscribe. Share with your friends because this is a made up question, so they probably won't be able to find it. If you got questions, comments, or if you find a mistake, leave it in the comment section. I will get back to you as soon as possible. If you want to support me, become a member or drop a super thanks. Until next time, see ya.